Stars are born in giant clouds of gas and dust. Then they spend their lives fusing hydrogen into helium in their cores. And when they die, some explode as supernovas, scattering the building blocks of life across the galaxy before fading away into a black dwarf. But how do we know this? How did we figure out the life cycle of a star? And what does it mean for stars like our Sun to go through this entire process? Well, let's take a look at the science behind how stars live and die. First, we have to look at where stars are born. Stars form inside giant clouds of gas and dust called nebulas, and these can be pretty huge. Our Sun is about 860,000 kilometers from its closest neighboring star, Proxima Centauri. And if both stars were placed inside the largest nebula in our galaxy, the Eagle Nebula, they would still only occupy about 10 millionths of its volume. These giant clouds of gas and dust are mostly made of hydrogen and helium, the simplest and most abundant elements in the universe. And although we think of space as being empty and dark, these giant clouds are actually opaque and brightly colored. They just don't reflect much light because there isn't anything around that's emitting any. So where does all this light come from? The answer is stars, lots and lots of stars. Stars produce light by converting mass into energy through nuclear fusion. When a cloud of gas and dust collapses and begins to shrink, the density and temperature at its core increase dramatically. And when it gets hot enough, nuclear fusion kicks in. This is what powers our Sun and every other star in the sky. But before stars can shine, they need fuel. And the most abundant fuel in the universe is hydrogen. The simplest type of nuclear fusion that stars use is called proton-proton chain, and it converts 4 hydrogen atoms into 1 helium atom while also releasing energy in the form of light and heat. So the first step in a star's life is taking hydrogen and turning it into helium, which also releases energy. In fact, the main sequence is really just a fancy name for stars that are actively converting hydrogen to helium in their cores. Our Sun has been in the main sequence for about 4 billion years now, but it will run out of hydrogen fuel in about another 5 billion years. When a star runs out of hydrogen in its core, it can't fuse anymore, so it stops producing light and heat. And without the outward pressure that nuclear fusion provides, gravity takes over and the star collapses. Exactly what happens next depends on the mass of the star. Stars less massive than our Sun become red giants. As the star collapses, the core gets even hotter and denser, and the outer layers expand, cooling the star down so it glows red. These stars are literally millions of kilometers wide, but they're not very massive. So the material they're made of isn't very tightly packed. In fact, the star is so big that it loses its shape and becomes what astronomers call an amorphous blob. Eventually, the star ejects most of its outer material, leaving behind a small, dense core called a white dwarf. Unlike the giant star it once was, the white dwarf is very small and doesn't emit much light. It's essentially just a dead star. However, it's still hot, so it glows white as it slowly cools off over billions of years. Eventually, it fades away to become a black dwarf. No light passes through a black dwarf because it's completely opaque. Unfortunately, no black dwarfs have been discovered yet, probably because they're too dim to see. For a star like our Sun, this is the end of its life. But more massive stars have a lot more fuel to burn and go through a different series of changes when they run out. Stars more massive than our Sun become red hypergiants. As with red giants, they start out as blue stars, but as they collapse, the core heats up and the outer layers expand, turning the star red. However, unlike low-mass stars, high-mass stars have enough energy to undergo further nuclear fusion in their cores. They convert helium into carbon and oxygen and release even more energy. These new elements are heavier than iron and create a growing core of heavy elements called an iron core. This process of creating heavier and heavier elements in a star's core doesn't release energy. In fact, It requires energy. So as the star continues to collapse, the core gets hotter and hotter. And when it reaches about 20,000 kelvins, something incredible happens. All the elements in the periodic table, except iron, are unstable. So as the core of a high-mass star gets hotter, the atoms are forced to break apart, releasing even more energy. All this energy creates a gigantic explosion called a supernova. When a star explodes as a supernova, it ejects most of its material into the surrounding interstellar space, leaving behind only a small, dense core. If the star's core is less than 1.4 times the mass of the Sun, it becomes a white dwarf. But if it's more than 3.1 times the mass of the Sun, it becomes a neutron star. Neutron stars are extremely dense, packing more than 2 times the mass of the Sun into a sphere only 20 kilometers wide. To put that into perspective, if you took the entire Earth and squeezed it hard enough to make it the size of a neutron star, its mass would be greater than 100 trillion. What makes neutron stars so dense is that their matter has been squeezed together so tightly that electrons have been forced to combine with protons in the nuclei of atoms to form neutrons. The remaining neutrons are packed so tightly together that not even light can escape their gravitational pull. This means that neutron stars are technically black holes, but we can still see them by observing the material around them. Just like white dwarfs, neutron stars can exist in binary systems where they orbit around each other. And these systems are actually the best places to look for exotic objects like neutron stars and black holes, because their gravity is so strong. They can pull things out of their binary partners and accelerate them to almost the speed of light. And when fast-moving material from a binary partner strikes the surface of a neutron star or black hole, it emits X-rays. So astronomers can detect these objects by looking for bright X-ray sources in binary systems. Finally, there are stellar remnants that aren't white dwarfs or neutron stars. Stellar remnants can also be black holes. Black holes are regions in space where gravity is so strong that nothing, not even light, can escape their gravitational pull. You might be wondering what happens to the material ejected during a supernova. Because it contains heavy elements that wouldn't exist without the star's explosion. This material is rich in nutrients like nitrogen, oxygen, phosphorus, and iron, which are necessary for life. As a result, supernovae are sometimes called the engines of life, since they scatter these building blocks of life across the galaxy. After a supernova, these materials gather together to form new stars and planets, allowing life to flourish throughout the galaxy. Unfortunately, supernovae are pretty rare events, so astronomers rely on computer models to help them understand how stars evolve. One such model is the Geneva Code, a set of equations that describe how stars produce energy and evolve over time. The Geneva Code was developed by a team of astronomers led by Professor Georges Maynet at the University of Geneva. It's named after the city where the code was developed, rather than the Geneva Convention. And it's used by astronomers around the world to study how stars live and die. In fact, the Geneva Code was used to create all the animations you saw in this video. The code is publicly available, so anyone can use it to study how stars evolve. And there are already plans to use it to study how stars form in multiple dimensions. Our sun will never explode as a supernova because it's not massive enough. But that doesn't mean that it won't leave behind a stellar remnant. In about 5 billion years, the sun will run out of hydrogen in its core and turn into a red giant. It will engulf Mercury, Venus, and probably Earth, but luckily, it won't destroy the solar system. After the sun ejects most of its outer material, it will leave behind a small, dense core that could be up to 10 times the mass of Earth. This core could be either a white dwarf or a neutron star. We don't know exactly what will happen because it depends on whether the sun forms a binary system with a planet like Jupiter. If it does, then its remnant will be a white dwarf. But if it doesn't, then it will be a neutron star. Either way, the remnant will be very small, less than 100 kilometers in diameter. To put that into perspective, if you squeezed the entire Earth to make it the same size as the Sun's future remnant, its mass would be greater than 50 quintillion. Now watch what happens when a massive star goes supernova, or check out this video instead.